When you're carrying out binomial expansion for year 2 A-level maths, where n could be not just a positive integer, but any rational number, it could be positive, could be negative, could be a fraction, could be a negative fraction, then the process to follow is going to have some similarities with year 12, but there'll be a few key differences. What I would suggest is that you try to break it into 3 steps. And it might be that you do these 3 steps in the order that I'm showing them, or it might be you do each step for each individual term as you go along, which might end up being a bit quicker. But if you can break it mentally down into 3 different pieces, you'll be much less likely to miss things about each piece because you'll have a focus on each part as you go. The first bit is the coefficients themselves, and these will always correspond to the values n, and they're going to look like the beginning of a factorial. But because n is likely to be a fraction or a negative number, they won't appear quite the same as, I don't know, 5 times 4 times 3. If n is a half, for instance, you'll have 1 in the first term, and you'll have half in the second term. Then you'll have half times minus a half, and then the next term is going to involve a half times minus a half times minus 3 over 2. And I'd recommend writing them in that slightly simpler form, because trying to simplify minus a half take away 1 and minus a half take away 2 is going to be a lot more work later on. The next step is the x terms, or the coefficients of x, or in this case the coefficients of kx, because you're likely to have something else in place of x when you're doing your binomial expansion. Don't forget to include the brackets, because when you're raising kx to the power of 2 or 3, it's really important that you raise the entire term kx to that power and not just the x bit. So for instance, kx squared is the same as k squared x squared, as long as you remember the brackets. And the third bit is going to be the factorial denominator. And the factorial will always match the power of x that you've used. So for instance, we're going to have a 3 factorial in the final term we've got on the slide here. And even the first 2 with the 0 and the 1 technically correspond to 0 factorial and 1 factorial. Although, of course, 0 factorial and 1 factorial are both equal to 1. And even 2 factorial, you could argue, can be just written as 2. But I like to write it as 2 factorial to remind me, so that when I get to the next term, I don't forget that it's 3 factorial and accidentally write 3 by mistake. Once you've got all of those pieces, you're literally adding them all together, and that's your result. So next, we're going to have a quick look at what it looks like with actual numbers, so you can get a feel for this process, and then you can see how you can adapt it for yourself. But as I said, even if you use these 3 pieces, but you do it 1 term at a time as you work along, you're going to find it easier to not miss anything out. So let's try with 1 minus 2x to the power of minus 3. We start with the coefficients. We always begin with a 1. Then for this one, n is minus 3. N times n minus 1 is minus 3 times minus 4. And finally, minus 3 times minus 4 times minus 5. Then the power of x. And because we have a minus 2x, we need to make sure not just the x, but also the 2 and also the minus go inside the brackets. So that when we're multiplying by minus 2x in a bracket squared, we're actually multiplying by 4x squared. So the minus signs will have an effect as well. You need to make sure they stay in a bracket so you can see how they're going to be affected. And the final bit is the factorial denominator. And here I've written that in a simpler form so you can see if I'm dividing by 1, it's just a 1. If I'm dividing by 0 factorial, that's the same as dividing by 1. 1 factorial is 1, 2 factorial is 2, 3 factorial is 6. So you could write it as 6, or you could keep it as 3 factorial. It's kind of up to you. And the final step is, of course, the simplifying. So you add them together, and then you find a way to combine the terms. And probably, having gone back and forth on this a bit, I think on balance, I'd say using a calculator is going to be the most efficient way to not make mistakes, especially if you're using a calculator to work out the value of, say, the second term. Then to go from that value to the next one, it's relatively quick. You'll notice the 6 we got for the coefficient of x. The only extra pieces I need to take into account are we've got a minus 4, we've now got a 2 on the bottom, and because minus 2x is now squared instead of just raised to the power 1, we also have an additional minus 2 in there. So I'm going to take my 6, I'm going to multiply it by minus 4, I'm going to multiply it by minus 2, and I'm going to divide by 2, and the overall effect will be 24. And a similar thing for the next term, because all of the terms in each piece will correspond to terms in the next bit, but with some extra pieces. The extra pieces here are a minus 5 another minus 2, and the 3 from the 3 factorial. If you think about it, when you go from, say, 2 factorial to 3 factorial, really all you're doing is multiplying by 3. Just like if you go from 5 factorial to 6 factorial, you're just multiplying by 6. So if you take your 24 and you multiply it by minus 5, and then by minus 2, and then divide by 3, you will get to 80. So that's a fairly quick way to do that with a calculator. It's worth remembering what happens when you have something other than x in your expansion. The general formula says 1 plus x to the n, and what I've got written here is 1 minus 2x to the n. So what I would suggest is you write out the limits of validity, the mod x is less than 1, in terms of just a straightforward two-sided inequality, so a sort of, I suppose, three-sided inequality. X is between 1 and minus 1. And if you replace x with minus 2x in this three-sided inequality, you'll find you can divide by 2. The minus sign, if you divide by minus 1 as well, that's going to flip all the signs, but it also changes your 1 to a minus 1 and your minus 1 to a 1. So basically, you can ignore the minus when you're dealing with a modulus inequality like this, in a sense, because all we're interested in is the size of that x term, or in this case, the size of 2x. So as long as we know that that's what's happening, we can then divide everything by 2 to get back to x. And at the end, we're simply saying that x is between half and minus a half. Next, we're going to have a look at how we can use binomial to approximate things that would otherwise be quite time-consuming and tedious to calculate. So in this particular case, we're going to find an approximation for root 5. Essentially, what we're doing is taking something that will be difficult for humans and indeed for calculators and computers to compute, like square roots and reciprocals, and finding an alternative calculation that's much, much quicker and easier to do, which even a computer will benefit from, because if it needs to do many, many, many of these calculations in a very short space of time, but it doesn't need infinite precision, it just needs a certain level of accuracy, then this is a very good alternative approximation. The trick is to, first of all, be able to carry out the binomial expansion. And in this case, that means looking at that weird expression on the left and recognizing that you could rewrite it in this form. Be careful with this. A lot of people will think, well, I can turn that into 1 plus x to the half divided by 1 minus x to the half. And although that's a valid way of writing it, it doesn't help very much with turning it into a nice looking polynomial, because even if you do binomial expansion of the top and the bottom, you'll still have a polynomial divided by a polynomial. Whereas with this method of taking that power of a half from the bottom term and writing it as multiplying by something to the power of minus a half, we will end up with a binomial expansion for each of those two pieces, which we need to multiply together. And although that might sound impossible, multiply two infinite polynomials together, if we're not caring about anything higher than x squared terms, it's not that tedious. You just multiply the pieces that you care about, and anything that would give you x cubed or higher, you can ignore. So let's assume you've done that. You've calculated the binomial approximation. It's come out as 1 plus x squared over 2, at least the first three terms. And now we're going to do the next bit. It says, let x be a ninth and find this particular approximation for root 5. Now, obviously, we know, and you can even prove, that root 5 cannot ever be written as a fraction. Not this one, not any other fraction. We can prove that by contradiction. But what we're doing here is not a pure mathematical proof that root 5 is actually an irrational number. We're saying from a practical perspective, if I need to know what root 5 is approximately, essentially what the calculator does when we ask it for a decimal approximation, then is there a nice quick way to get a rough answer? So the first step is to substitute x equals a ninth into the left-hand side, because although you might assume that just plugging in a ninth is going to give you root 5, that's not how it works. And a lot of the time, you'll get something that's related to root 5, but not quite the same as root 5. In this case, for instance, if you put 1/9 into the left-hand side, you get the square root of 1 plus a ninth divided by 1 minus a ninth, and that will simplify down to root 5 over 2 eventually. which means that what my binomial expansion has given me is a way of approximating half of root 5, which is just as useful because once I've got an approximation for that, I can double it and I'll have an approximation for root 5 itself. The next step is to substitute a ninth into the right-hand side. And this is reasonably quick to do, and of course you can use your calculator to help, and it simplifies down to 181 over 162. And then we equate those two, but be careful with this. We're proving that these two things are approximately the same, so avoid an equals sign, use the approximately equals sign instead. If a half of root 5 is roughly 181 over 162, then root 5 itself is roughly double that, 181 over 81. And it's not a bad idea at this stage to double check if you've been asked to approximate something, is your answer reasonably close to the thing it's been attempting to approximate. And in this case, 2.236-ish is the more accurate value of root 5. Our approximation comes out as 2.234-ish, so it's not far off. Just briefly, if you're curious about why computers need to be able to do this so efficiently, you might want to look up the fast inverse square root method that a programmer came up with. It involves initially ideas like this and approximation methods for a workaround, so we don't actually have to calculate square roots, but it has some other clever stuff going on in terms of bit shifting and whatnot that can happen when all your numbers are in binary. So if you're interested in seeing what it looks like from the perspective of a computer where a graphics card has to do millions of these calculations in a very short space of time, then have a Google of that one. The next thing is a few questions using this idea on approximations. I'd encourage you to pause the video, have a go at these questions, and then come back when you've tried them to see if your answers match. So for the first question, the first four non-zero terms, basically that means we're going to need the constant, the x term, the x squared term, the x cubed term, and that should be enough. So I'm going to use the approximately equals sign. You could also just say equals and then have plus ... at the end. The values for which the expansion is valid, this comes from substituting in the x term that we have into mod x is less than 1. We need the size of the x term to be no bigger than 1, but in our case the x term is actually that minus 2x that's inside there. Since it's about size, you can safely ignore the minus for this, and if 2x has to be between 1 and minus 1, then x has to be between a half and minus a half. Now for the next bit, if you substitute 0.1 into the expansion, well, on the left-hand side, you'll get something which eventually simplifies to 2 root 5 over 5. And on the right-hand side, you get something that evaluates to 0.8945. And because we've got 2/5 of root 5, if we want to convert that into an approximation for root 5 itself, we're just going to multiply by 5 over 2. And that gives us 2.23625, which is a pretty good approximation. If you want to work out the percentage error, then the method for doing that is to either, there's a couple of ways, but you could calculate the actual absolute error. In other words, how far away is this number from root 5, and then divide that number by root 5. Or you could just divide that number directly by root 5 and then interpret your number as a percentage change. So if you would have to multiply root 5 by 1.00008, it means there is a 0.008% error. So that's what we're dealing with here. For the bonus question, if you got to this, you can actually use the same binomial expansion to approximate a whole different irrational number. The trick is to substitute in 0.01, and you'll find that the left-hand side now evaluates to 7 root 2 over 10. The right-hand side gives you something very, very close to 1. And the beauty of this one is that because x is so small and so close to 0, the approximation is incredibly close to the real thing. And after we multiply by 10 and divide by 7, we get 1.414213571, which is an error of a very, very, very small percentage. Next, we're going to briefly talk about how we can modify the binomial expansion formula so that it can work even if the contents of the bracket is not just 1 plus something, but it's something plus something. In other words, instead of 1 plus x to the n or 1 plus 5x to the n, we've got a plus bx to the n. So we might have, for instance, 3 plus 5x to the power of minus 2. And it turns out there's a nice quick workaround for this. We can reduce this to a problem we already know how to solve by recognizing that 3 plus 5x can be factorized. We kind of force a factor out of this because we're going to leave ourselves with some fractions in most cases, but that's okay. I would like to write 3 add 5x as 3 multiplied by 1 add 5/3 of x. But in order to do that, I have to remember that the power of minus 2 now applies to both of those terms. So step 1, take out the 3. Step 2, don't forget to apply the power of minus 2 to both the 3 and the remaining bracket. And you should find that everything in the bracket has been multiplied by 3, which includes the bit with the x. And at the end, if we've done it properly, there should now be a 1 in the front of the bracket. The mistakes that people commonly make, either when they divide by 3, they don't divide both terms by 3, or when they take out the 3, they forget to put a power next to it, or having done all of that correctly, they perform the binomial expansion and then they forget to multiply by 3 to the minus 2 at the end. So watch out for that. I'd recommend you put 1/9 at the front in a case like this, and a pair of massive brackets. You do your binomial expansion inside your brackets, but you've still got the 1/9 written in front so you don't lose it along the way. A good thing to check is that you understand how you would apply this method when you're asked about the limits of validity. And the thing to notice is that, in fact, having applied this fix, you end up with a problem which is the same type of thing you've dealt with before. So for instance, if we had 1 plus 5/3 x, then 5/3 x is the thing that has to be between 1 and minus 1, which means x itself has to be between 3/5 and minus 3/5. And you could do the same thing with, say, the 3 minus 2x example. You would have to pull out a factor of 3, leaving you with 1 minus 2/3 x inside the bracket. And that means that 2/3 x, or minus 2/3 x, has to be in size less than 1, which is equivalent to saying 2/3 of x has to be between plus and minus 1. So x has to be between plus and minus 3/2. Now you've got a couple of exam questions to have a go at. Both of them follow a similar format. You're going to perform a binomial expansion, and having done so, you're going to make use of your expansion to calculate an approximation for an irrational number. In one case, it's the 4th root of 80. In the other case, it's the cube root of 2/7. When you've done that, there are a few extra questions from the textbook that you can try on a similar theme if you want more practice. Let's look at the mark scheme for this question and see where you're going to pick up the marks from. In the first part, the 2 marks are basically for a correct method and a correct answer. The correct method should have broadly the correct things. You're looking for getting the x term in brackets, so you're squaring the minus x appropriately. And you've got the correct terms like the n, which is a quarter, and the n minus 1, which is minus 3/4. They would accept a sign error, as you can see in the comments here. So if you've got a positive instead of a negative, you would still get the mark potentially there. And they will also allow an incorrect coefficient of x squared. You'd still get the method mark, but you wouldn't be able to get the answer mark. What they've said here about equivalent fractions or decimals means that as long as you've written exact values, you'll be okay. Just watch out for this, because if you end up with a fraction of a third and you just write 0.33, that's not the same number. So you're not necessarily going to get the mark because you don't have the exact value. In general, I'd suggest sticking with fractions. For the second part of the question, there are 3 marks available, and it's a show that question. In this case, the examiner needs to be convinced that you know what you're doing, so you've got to demonstrate where this comes from. And the first step is what we've seen before, pulling out a factor of 81, so that you have 81 to the power of a quarter multiplied by 1 minus 16/81x to the power of a quarter. That's where your first mark comes from, demonstrating that you can do that. And then you can make use of the previous part of the question. Not only is this part of the same big question, but it's part of the same question part. It's part of question 1a because it's just part II. And they've used the word hence, which means you have to make use of the previous bit. What they're looking for here is that you recognize you've already got an expansion for 1 minus x to the quarter. And now we need 1 minus 16/81x to the quarter. So all that you need to do is go back to the previous expansion that you calculated and replace x wherever it appears with 16 over 81x. Just remember that when you square it, you square the whole thing. And that's all that's happened here. Once you do that, you should end up with the appropriate thing. They've allowed any other number that you might accidentally have written in the front. Perhaps you've miscalculated 81 to the quarter or something, but as long as you've got a number there, you're still going to be able to get that second mark. And the final mark here, you have to have the fully correct answer. So you've got to recognize that 81 to the quarter is 3, and then you multiply through everything by 3. You should be able to write it in the format they've given. And the final part of the question, which can be a very quick 2 marks once you know what you're doing, using your result to find an approximation for the fourth root of 80. Notice that we have a bracket with a power of a quarter. So if the inside of the bracket could be made to be equal to 80, then you've got an approximation for 80 to the power of a quarter. So that's all we have to do. 81 minus 16x would have to be equal to 80, which means 16x has to be 1, which means x should be a 16th. And using x equals a 16th is how you get your first mark. It says use it, so not just writing it down, but actually making use of that value, substituting it into your binomial expansion. And they've just shown the right-hand side of the expression because it should be fairly clear that the left-hand side gives you exactly the thing you're trying to approximate, which is the fourth root of 80. So that gives us a number, and they've also asked for it to 7 decimal places, so you wouldn't get your answer mark unless you've written exactly 7 decimal places. The only other thing I would suggest in this one as well is that you could try calculating the fourth root of 80 on a calculator to see how close you are. But of course, the fourth root of 80 is just going to be very slightly below the fourth root of 81, which is why this number is coming out so close to 3. In this question, the first part gives you 3 marks. The reason they give you 3 marks rather than 2, which is more common for binomial, is that you have to do a couple of steps. You've got to make sure you can convert this into a format where the binomial expansion formula applies. So step 1, take out a factor of 27. And don't forget to apply a power of minus a third to both the 27 and the remaining bracket 1 plus 6 over 27x. Then you carry out the binomial expansion for the bracket that's left behind, and there's a mark for pulling out the 27, there's another mark for doing the binomial expansion, and the final mark for correctly putting it together and getting the correct answer. The second part of the question is for finding the appropriate approximation. They've already told you that the cube root of 2/7 is equivalent to 2 divided by the cube root of 28, so that's your clue. Our bracket is a way of calculating 1 over the cube root of something because it's a power of minus a third. So if the stuff inside the bracket was 28, then we would be calculating 1 over the cube root of 28, which is exactly half of what we need to calculate 2 over the cube root of 28, which will be the cube root of 2/7, which is what we're looking for. So we need to make 27 add 6x equal to 28, which means making 6x equal to 1, which means x has to be a sixth. And if you substitute 1/6 into your formula, then you should be able to get an approximation from the right-hand side, which corresponds to an exact value on the left-hand side. So the two things are roughly the same, but the exact value that you're approximating will be 1 over the cube root of 28. And therefore, the final bit is to recognize that the number you get, 0.32 something, is only half of the number you want. So you double it, and then you write your answer correct to 6 decimal places, 0.658639.